Good morning. I'm Jane Platt with the Media Relations Office at NASA's Jet Propulsion Laboratory in Pasadena, California. We're all counting down to the very big and dramatic day on Mars that's coming up 3 days from now. This Sunday, August 5th Pacific Time, or August 6th in the Eastern Time Zone, NASA's Mars Science Laboratory and its rover Curiosity will land on the red planet. This is an extremely challenging and ambitious mission, and we're going to find out more about it, and we're going to get the mission status and a preview of the entry, descent, and landing in this news conference, and we're going to find out all about the things that have to happen in the next few days. I'd like to introduce our panelists first. We have Doug McQuistion. He is the Mars Exploration Program Director with NASA headquarters in Washington. We have Pete Teisinger, Mars Science Laboratory Project Manager at JPL. Also from JPL, we have Adam Steltzner, the Mars Science Lab Entry, Descent, and Landing Phase Lead. And we have Thomas Martin-Muir of the Mars Science Lab Navigation Team Chief at JPL. Ashwin Vasavada is the Mars Science Lab Deputy Project Scientist, also of JPL. And we will also hear from Doug Ellison, who is a visualization producer here at JPL. Let's get things started with Doug McQuistion.
Okay, thank you. Well, it is an extreme pleasure to be here. It's been a lot of years we've been working on this mission, and we're almost there. This is great stuff. I'm going to talk about something a little bit different today. I'm going to talk about how big this mission really is. MSL has a huge reach. Reaches back into the past, it reaches out into the future, and frankly, it reaches around the world. If I can have the first graphic, please. MSL is not just a randomly selected mission plunked down in a 2011 launch time frame. It was a carefully selected mission in the middle of a program that has been a series of strategically selected and decided missions for the past 10 years. It's built on and forged by the discoveries of the past of missions such as Odyssey and Mars Express, Mars Reconnaissance Orbiter, and the technical capabilities developed since Pathfinder and through the Spirit and Opportunity rovers. It reaches across thousands of people and many different countries around the world. It reaches all the way around the country, frankly, and has been a powerhouse here on Earth economically. It's employed in excess of 7,000 people in good, high-paying technology and technician and science jobs. It's reached 37 different states of the Union, and a little bit, appropriately, like the Olympics, it's reached a number of foreign countries. There's nearly 10 countries that are involved in this, and 5 of them are major partners: Spain, Canada, France, Germany, and Russia. Plus the European Space Agency itself with Mars Express that's helping us with communications and some other science, obviously, in shaping how this works. So I hate to, but I will, compare it slightly to international gymnastics in that it is going to be a tough series of challenges here for the team to get this to the surface, but at the end we're all going to stick the landing, right, guys? MSL reaches from the past decade into the next decade as well. If I could have the next graphic, please. Maven, 2013 launch, is the next in this strategically selected program. This is a very important mission. You heard from the science panel before about Mars past. One of the questions about that is how did it go from having a warmer, wetter past to the dry, somewhat barren planet we see today? Maven is actually a decadal survey-inspired mission from the first decadal survey that Mars was in that will go help us understand what happened to the atmosphere of Mars and what happened to the planet's water-related past. It's also unique in the fact that it's the first Goddard Space Flight Center-led mission and built by Lockheed Martin. MSL gives us a range of capabilities for missions after Maven as well, from small scientific analysis type landers to human-scale precursor missions, hopefully beginning in the 18 and 20 timeframes. If I could get the next graphic. One example of this is an instrument called Medley, which in what you see here is actually the Msl Heat Shield with technicians around it installing some of the Medley sensors. What these sensors do is measure pressure, temperature, and actually the recession rate of the thermal protection system during entry. Since this heat shield is nearly the size of the Orion capsule's heat shield, and therefore could actually be very similar to what will eventually get humans to the surface of Mars, we will learn an enormous amount about what it takes on a guided entry vehicle, what the impacts are on the thermal protection systems, and what the atmosphere looks like in a vertical profile. This, coupled with the RAD data that Don Hassler talked about a few minutes ago, really pushes us further into the future with the potential for humans to Mars and really helps. And then the ability to get a metric ton to the surface is nothing to sneeze at either, whether it's resupply or other things related to the need for humans and other future precursor missions. As we forge a path forward, everything is critical. Orbiters are critical for reconnaissance and communications. Landers are critical for in situ analyses, returning samples, and potentially even humans to the surface. But moving back to MSL, at the L-30 press conference, I mentioned that Odyssey had an issue with the reaction wheels and was out of place in phasing to be able to communicate the landing process. I am very pleased to say that that team has done a great job, moved Odyssey back to where it should have been, where we planned to have it all along. And they're running tests and even some data flows to make sure that all systems are working normal. It's looking good. The Mars Reconnaissance Orbiter is looking good. There's some additional testing going on that, but polling of the teams is going on, and I think by tomorrow, which is the plan, we will be in full swing for communications capability for MSL. So just in case you missed it, live under a rock or whatever, we're about to land a small compact car on the surface with a trunkload of instruments. This is a pretty amazing feat getting ready to happen. It's exciting, it's daring, but it's fantastic. Mars Science Laboratory's reach is about to touch the planet Mars, only 3 days and about 12 hours from now. So with that, I think you want to hear about the mission and how it's doing. I'll pass it over to Pete.
Thank you, Doug. Well, the mission's going extremely well. You'll hear from Adam about EDL preparations and EDL, and from Martin about navigation, and Ashwin about the atmosphere and Mars and the weather, but everything is really on track. So the spacecraft is behaving perfectly nominally. We have no anomalies to work. Everything is in the green across the board. So we are really good to go 3 days out. It's very, very quiet in my office, which is good to have happen. I just wanted to say a couple thank yous. We've gotten great support this summer in preparation from our sister projects, from Odyssey and from MRO and from MEX in their preparations to support us for communications, not only during this critical EDL period, but also throughout the mission. And also our brethren at the DSN who've done a great job in supporting us to get to this point. We've all done a lot of training exercises this summer, and we've done those have gone very well. I think my deputy pointed out that you're done with the training exercises when you don't want to do another one, and we are certainly there. So we're ready to go for real on Sunday night in Pasadena and Monday morning on the East Coast. And I'll let you, Adam, talk about EDL.
Thank you, Pete. Well, as Pete mentioned, things are looking good for Sunday night, and we're excited. There's a very talented team of folks who have put this EDL system together and invested an awesome amount of their time. There's over 300 years of human individual contribution to this EDL system, and we're very excited for a chance to test its mettle on Sunday night. If you roll the video, I'll take you through briefly some of the elements of our EDL system, or entry, descent, and landing. We start prior to the atmosphere of Mars, about 13,000 miles an hour. And we are at this point, we separate the cruise stage and prepare for running into the atmosphere of Mars. It's a bit of an impact. We will pull about 10 Earth Gs or more of acceleration during our first contact with the Martian atmosphere. During that time, we're employing something called guided entry, which I'll speak a little bit about later. But we'll be using our reaction control jets, which you can see in this video occasionally firing at the back of the spacecraft to help Curiosity steer her way through the atmosphere. After we've gone through that hypersonic entry phase, We adjust the attitude of the spacecraft by throwing off some masses and prepare for parachute deploy. We open this parachute a little bit less than Mach 2, or about 1,000 miles an hour at Mars. We open up the world's largest supersonic parachute, 21-meter diameter parachute, and then almost immediately remove the heat shield and start looking for the ground. At about a mile above the surface, we will have seen the ground with a custom-made radar, landing radar, and we will let go of the parachute and use our 8 Mars landing engines, also developed purposefully for Curiosity. We'll use those rocket engines to slow us from about 200 miles an hour down to about 1.5 miles an hour, or 3/4 of a meter a second, and in straight vertical flight. We're in that straight vertical flight for the last 200 meters or so, looking straight down on where we're going to land. And then 20 meters before we land, we separate the rover below the descent stage, and the two together continue at that 1.5 miles an hour down gently towards the surface until Curiosity herself weight is taken up by the terrain of Mars. At this point, we cut the descent stage free, and it flies off to a safe distance to impact the surface. Leaving Curiosity, wheels down on the Martian terrain, ready to begin its surface mission. Now, there are two key novel pieces to this entry, descent, and landing architecture. The first is guided entry, and I mentioned that. I'll walk you through a bit of it. Historically, the landing footprint that our missions have been 100 kilometers or more of landing uncertainty when we go to select the site that we're going to. Well, it's quite hard to find safe sites to land that are that size. Curiosity uses guided entry to shrink that from 100 kilometers or so down to something a skosh less than 20 kilometers of uncertainty. To do that, we take our entry capsule. We have some masses, about 1 MER's rover worth of tungsten in 6 ports out here. And when she flies through the atmosphere of Mars, because of these weights, she flies at a canted angle. That canted angle develops lift. She then uses the reaction control jets here to turn that lift vector forward and backwards, up and down, to control her descent through the atmosphere and remove both errors in delivery, although Tomas is not going to give us any errors in delivery, and more importantly, the uncertainty of the atmosphere that we may encounter on the day we land. That's always been traditionally a big question mark. What atmosphere are we going to find when we come in? This system allows us to be robust to a large range of those possible atmospheres. The second big novelty, and you may have noticed this, is the way that we touch Curiosity down to the ground, the touchdown system or landing system. 20 meters above the surface, Curiosity still has her jet backpack, the descent stage, strapped to her. She's in vertical flight. And at this point, she's lowered by the descent stage. As they both continue downward, she's lowered down on a 7.5 meter bridle. And the two together slowly make their way down until her weight is taken up by the terrain of Mars. At this point, with Curiosity safely on the surface, and after we've acknowledged that the weight is gone, the descent stage cuts itself free and flies away. It looks a little bit crazy. I promise you it is the least crazy of the methods you could use to land a rover the size of Curiosity on Mars, and we've become quite fond of it, and we're fairly confident that Sunday night will be a good night for us. Thank you. Now Tomas will tell you how we're going to get there on time and to the right spot.
Thanks, Adams. That's a very difficult task to follow. Curiosity is currently about 670,000 miles from Mars and is approaching the planet at a speed of just 7,800 miles per hour, not as fast as it will be when it enters Mars. Since Curiosity was launched by an Atlas V rocket back in November of last year, the navigation team has been using the tracking data from the antennas of the Deep Space Network to determine where Curiosity is and where it is going. The navigation team has designed trajectory correction maneuvers that have adjusted Curiosity's trajectory so we'll enter Mars at the right point, so it can safely and accurately be delivered to the Gale crater. The mission control team has executed so far 4 trajectory correction maneuvers, and the last one was successfully executed last Saturday evening. First image, please. Here you can see a picture of the surface of Mars. You can see the entry point in which we enter the atmosphere. So we enter at an angle of minus 15.5 degrees. And then the ground track of Curiosity as it descends into the surface of Mars and the touchdown point in the north side of the Gale crater. You can also see the ground track of the Mars Reconnaissance Orbiter as it will fly over Curiosity and provide communication support. Next image, please. Here you can see where we were going to enter the atmosphere of Mars before the maneuver that we executed last Saturday. The entry target, that was the target for that maneuver, the onboard state that we put in the spacecraft last Monday, and our latest estimate that we have calculated 3 days later. So the maneuver moved us by about 13 miles. We are now about 100 yards, 1,000 yards from the entry target. And the difference between the latest estimate of the onboard entry point, and the onboard state is just below 200 yards. The main task of the navigation teams over the next few days up to landing is to keep processing the tracking data from the Deep Space Network so we can accurately predict this entry point, and if necessary, send an update to the spacecraft. The other task is to determine any maneuvers that may be needed, but it seems that based on the results that you are seeing, we may not need to do the maneuver that was planned for tomorrow. The navigation team needs to tell Curiosity where it is as it enters the atmosphere of Mars so it can find its way to the Gale crater. There is no GPS in Mars. We have to track Curiosity from the antennas in the Deep Space Network in the Earth to tell it where it is as it approaches Mars. It is like driving to work just by looking back in the rearview mirror to the antennas of your house. Then next, Ashwin is going to tell us about the weather in Mars.
All right. So as Adam mentioned, we care about the navigation accuracy and then what weather occurs on Mars when we enter. And Tomas is delivering us right down the middle, but there's nothing I can do about the weather on Mars except predict it and then design the spacecraft to be able to handle all those potential conditions we can encounter. So that's what we've done the past few years. We're interested in understanding the weather on Mars, and we've been studying it for several years now to design a system that can tolerate pretty much everything Mars is known to come up with at this season. If we see any extreme weather in the next few days that even pushes the limits of what we designed the spacecraft to, we at least want to know it's coming so we can understand how that might affect the accuracy at which we land. So you might wonder, how do we predict the weather at Mars? Well, I'm going to turn to the live Doppler 8000. Actually, can't do that. I wish we had that on Mars, but really what we have is a spectacular weather satellite up there now. It's actually doing a lot more than measuring the weather. The Mars Reconnaissance Orbiter. So in the first graphic shows the Mars Reconnaissance Orbiter doing two things. It's looking down at the surface, taking both temperature measurements and taking color imagery of the surface, just similar to weather satellites would do on Earth. The temperatures in the atmosphere of Mars are related to the density, and the density, the thickness of Mars' atmosphere, is what will catch the spacecraft when we arrive at Mars. You can see also that MRO is looking ahead of itself and looking kind of at the atmosphere in its thickness, and that allows us to get very accurate temperature distributions with height, which we then turn into densities that we use to simulate our landing many thousands and thousands of times. So I'd like to show you a global weather map of Mars. But to orient you, I'd first like to show you this similar map of Earth. So this is the kind of format we'll be using in our maps of Mars, sort of unfolded, unwrapped the sphere of Earth onto this weather map of Earth, the beautiful planet. I'll draw your eye to just above Australia there, where there's a little ring, just over Indonesia. And that's exactly the same location on Mars where Gale Crater is, our landing site. So if we now go to the map of Mars, this was taken just 2 days ago by the Mars Reconnaissance Orbiter, the Mars Color Imager on that spacecraft, and it shows Gale Crater as well as some other features that we're interested in. When we arrive at Mars, it's coincidentally about August in the seasonal cycle of Mars, and that means it's just coming out of winter in the southern hemisphere, and Gale Crater is just slightly in the southern hemisphere. We expect this to be a cold time of year. It's when Mars is further away from the sun than at other times of year. And because of that, we see a lot of water ice clouds on this map. That's a good thing. We expect, we've modeled and predicted from past years that Mars will be nice and cold and clear and covered with this water ice haze when we arrive. And our latest map of Mars does, in fact, show that. The thing we do worry about a little bit is our dust storms. Now, we've designed the spacecraft to be tolerant of all the dust storms that have occurred in previous years. But as I mentioned, we do want to understand if there's a chance of dust storms occurring on landing day, because they may kick up extra winds that would cause us to land a little less accurately than we've been predicting. So just to make things interesting, on this map, there is a pretty healthy-looking dust storm at the bottom of the image. It's pretty far from Gale, more than 1,000 kilometers away. But it is kicking up dust in the atmosphere that has the potential to perhaps spread over to the site. Now, we're not worried about this particular storm. It's the kind of storm that tends to disappear within a day or two, and since this map is already almost 2 days old, we expect by Saturday, when I give you the next weather update, we won't even be talking about this storm anymore. So finally, oh yeah, I do want to show you also this interesting image from this is a close-up image of a similar small storm that was taken in 2007. Now, these dust storms occur on Mars at this season because the polar caps are receding back as we go from winter into spring, and there's a temperature contrast between the cold CO2 frost cap and the bare ground next to it. That temperature contrast stirs up winds that raises dust and creates these local dust storms, which you can see kind of boiling from the surface. Now, this particular storm was from 2007 and lasted less than 48 hours, and that's the kind of storm we saw on the image of Mars from July 31st, and we expect it to behave the same way. The final thing I'd like to share with you is that we don't only look at the weather in the atmosphere of Mars, we also look at space weather. Space weather occurs when plasma or high-energy particles leave the sun through coronal mass ejections or solar flares. Now, if these high-energy particles come from solar flares, they can reach Mars within only about an hour or two of leaving the sun. Why do we care about these things? These high-energy particles can impact the spacecraft in two ways. They can either cause errors in the memory of the spacecraft or cause stars that aren't really there to appear on the cameras that we use to track and navigate the spacecraft. Now, the spacecraft, of course, has been designed to be very tolerant to both of these effects. But again, we just monitor the environment around the sun using spacecraft around Earth and at Mars even, so we know what's coming, and so we have a good understanding of the environment the spacecraft will be in when it performs these very tricky maneuvers on Sunday night. So with that, we'll turn it over to Doug.
Thanks, Ashwin. For about 2 years, NASA's been sharing with the public the adventures that our robotic envoys have exploring the cosmos using a tool developed here at JPL called Eyes on the Solar System. Now, thanks to some fantastic data and support from Thomas and Adam's colleagues in the EDL and navigation teams, we're able to actually show you inside your web browser exactly what Curiosity is going to be doing over the next few days. What you're seeing now is actually a live view using Eyes on the Solar System, which you can get to just by going to eyes.nasa.gov inside your browser. It needs a reasonably modern computer, a Mac or PC, a desktop or a laptop is absolutely fine. And there are two things we can do here. One is that using this predicted simulation data provided by the Curiosity team, we can show you exactly where Curiosity should be right now. In fact, as Thomas mentioned, we're about 670,000 miles from Mars and doing just under 8,000 miles an hour. And you can track this, all the time, all the way through to Sunday evening. But because we already have this data, we can hit a magic button here that says Preview. And we can fast forward through to Sunday evening and see how things are going to unfold if things go according to plan. And so here we can see the spacecraft as it approaches Mars. And you can see the landing site way off on the limb right here. And on the night, if you're using the live mode, you'll be able to watch exactly what happens right inside of you like this. But we can actually skip forward. So I'm going to skip forward through EDL, and you'll see the exact same things that you'll have seen in the animation, but now you're in charge of the camera. You can stop, go backwards, forwards, look at it from any angle you want. As I fast forward through time, get closer and closer to the landing site, you can see the values screaming off on the side there, the altitude, the velocity, the distance to the landing site. You can see those guided turns that Adam talked about as we kind of guide Curiosity to the exact spot in the surface of Mars that we want to get to. And you can see a countdown to the different events on the right-hand side. I'm going to stop just after we get to the heat shield deployment, which comes up in just a few more seconds. There goes that ballast Adam mentioned. Here comes the parachute. You can see the beautiful parachute here. And you can see the countdown just down there. For a few more seconds, we'll see the heat shield come off, so I'll skip forward just a little more. There goes the heat shield. And at any time, of course, because it's a prediction, I can pause the action. I can go and have a look around. I can say, well, actually, I want to go and look at the heat shield. And here you can see the medley suite on the inside of the heat shield that was mentioned earlier. You can go back, look at the spacecraft behind us. And you can also see that this doesn't live in isolation. This lives in an engine that hosts the whole of the solar system. So behind us, you can see there's Mars Express. There's the Earth that's about to set about a minute after this moment in time. There's Mars Odyssey coming over the horizon, and towards the south, we can see the Mars Reconnaissance Orbiter. And if we want to look at things from over there, we double-click the mouse, and we can ride on board MRO and see that it's tracking Curiosity as it makes its way towards the surface. I can unpause the action. You can see MROs orbiting Mars. I can go back to Curiosity. And you'll see that 20 seconds after this moment in time, the Earth sets over the horizon. I'm going to fast forward just a little bit further towards the surface until things get really exciting. And now we see the spacecraft drop out of the back shell as it makes its powered descent towards the surface. I won't show you all the way to the end. I don't want to spoil it for you, but it's very exciting. And if things go according to plan on Sunday, then what happens should be very, very similar to this prediction you see right here. Everything I've shown you can do right at home inside your computer just by going to eyes.nasa.gov. And with that, I'll hand it back to Jane.
Thank you, Doug, and thanks to all our panelists this morning. We are ready for some questions from reporters here at JPL. If you do have a question, please raise your hand and wait for the mic to come to you. And let's start here in the third row, blue shirt.
Hi, Eric Han with Nature. My question is for Tomas. So you showed us the charts showing how the latest estimate was about 1,000 yards off from the intended target entry. Right. Does that mean that the center of the landing ellipse has shifted by that amount? And if you could also say what you'll use to decide whether or not that's too much and you need to correct for that in this window to do the correction maneuver tomorrow.
Want to take this on?
Sure. Because of the guided entry that we spoke about, errors in delivery of the spacecraft, like that 1,000 yards that we have, can be flown out by Curiosity on our way in. As accurately as Curiosity knows her location, she can control, to some fair degree, down to very accurately on the surface. So that 1,000 yards, if we were to choose not to correct it, we'll just let Curiosity correct it once she hits the atmosphere.
But you have to upload that software.
No. Nope. She knows where she knows the target that she's going to on Mars, and all that we have to do is give her our best estimate of where she is currently, and she'll do the rest as she flies through the atmosphere.
Okay, we've got a question there in the second row.
Hi, Irene Klotz with Reuters. Just to follow that up, what's the range then that the rover can correct for? And when would you be deciding if a TCM was necessary tomorrow?
So we've established a TCM criteria that's well within what her control authority is. What the range that she can clean up is tens of kilometers of error. But we would choose, very likely, if the spacecraft was healthy, to perform a TCM if we were just a handful of kilometers off of where we thought we were, because we want to stack the deck in her favor and sort of put her right down the middle so she doesn't have all that much to do when she gets to Mars.
And when would that decision be made, tomorrow or today, about whether to do the burn or not?
There's an opportunity to talk. We'll tomorrow, about middle of the day, we'll start making that decision.
Okay. And you really piqued my curiosity when you said that this landing system was the least crazy of the options that were on the table. Could you maybe pick one or two other scenarios that were not immediately laughed out of the room, and where you, what were kind of the trade-offs that led you to this system? Thanks.
Certainly. The leading two, the runners-up were maybe don't look that crazy to the layperson, but their performance and their risks throw them into the crazy category. They are legged landers, like we've successfully put on the surface of Mars in Viking 1, 2, and the Phoenix lander, also the Apollo landing system. They are not very stable. And when you stick a rover of the size of Curiosity on the deck of a legged lander, it becomes very unstable, and you need to land on a flat top spot to be able to make that happen. So that's where that one loses. And the other one was the airbag system that we've successfully used during Pathfinder and the MER's Spirit and Opportunity. Unfortunately, we don't have fabric here on Earth strong enough to build airbags that would work for a rover the size of Curiosity. And so the bags would shred, not giving Curiosity any protection, and that's what throws that one out.
Okay, we've got a question. Was that a hand I saw right next to Irene? Yes.
I read somewhere that one of the concerns about not landing the rover with the descent stage was that it would kick up so much dust it would foul up the equipment on the rover too. Was that a concern, or was that already outweighed by the fact that it would be unstable?
The issue of dust is certainly one. The issue of the interaction between the plumes and the surface is a very important issue. Dust is one of those. But actually, when you get a propulsion system close to the surface, you develop quite a bit of pressure that can make that landing terrain interaction very unstable. And so the way legged landers have approached that in the past is they come in very quickly, so that the guidance system doesn't have a chance to try and control it. It's more of it looks like a soft landing, but really it's a controlled impact. That has features that exacerbates the instability, and it also means that the computer has to look for a very quick signal of touchdown. And as some of you may know, one of the leading candidates for the reason we lost the Mars Polar Lander was it triggering off of a touchdown sensor some 80 meters above the surface and turning off its rockets and crashing to the surface. So in general, we don't like that technique either. So there's several reasons to keep the descent stage away from the ground, the first of which being remove that pressure and that instability, and then the dust is certainly a good thing to keep off the vehicle to the degree that we can.
Okay, and a reminder that if you do have a question, please raise your hand so we can get the mic to you, and also state your name and affiliation. Let's go to the back row right there. Conan.
Adam, much has been said on the internet about NASA's 7 minutes of terror. And this is obviously very sophisticated procedure that you're going through. Is there any particular minute of those 7 minutes that you are most focused on and most worried about?
Like any good parent, I love each of those minutes equally. In different ways, of course. They're all different minutes. Certainly, the novelty of the guided entry, and especially the novelty of the sky crane maneuver at the end, draw a lot of the attention of the team's anxiety. There's also that parachute that we use. It ends up being parachutes are fundamentally sketchy kinds of devices, right? The U.S. military troops jump out of airplanes all the time, and we've done amazing research about how to have them jump out of airplanes safely. But when they do, they take a second parachute. because with all that work and all that control, there's still enough uncertainty when you use a parachute that you would like to have a backup. Well, it ends up being you can't work a backup in this system, and so we have sort of a fundamental device reliability limit. We've done everything you can do humanly possible to improve our odds with that parachute, but that's sort of a fundamental irreducible risk about making it to the surface of Mars, is you got to use a parachute. So maybe sky crane, guided entry, parachute are 3 minutes of those 7 minutes that maybe take an extra bit of attention.
Okay, do we have more questions? Yeah, let's go to the third row right here in the maroon shirt. Craig?
Yeah, hi, it's Craig Cavalt with America Space and Aerospace America. Adam, and anyone else chime in too. Given lift and guided entry, would it be a correct analogy that you can relate this all the way back to Orville and Wilbur Wright's genius of first developing and measuring lift and control in the history of flight, taking it to Mars now?
Interesting question. I'm drawn towards nerding out with that question, so excuse me for doing that. The only thing that makes it tough for me to go there is that Orville and Wilbur were using Bernoulli lift from and we use a negative lifting body, or that is to say, we use blunt body momentum associated lift as opposed to Bernoulli lift. So whereas Orville and Wilbur fly forward and get lifted up, we sort of come crashing forward, pitch our nose down, and develop lift. You know, the Wright brothers, you pitch the vehicle up, it gets more lift. For ours, we get lift by pitching down. So aside from that, which sort of stymies me a bit, certainly it is use of lift. And we aren't the first. You know, we're using repurposed Apollo guidance algorithms that were used in the 60s and 70s. And we're using them novelly in an autonomous mission at another planet. It's also true that Viking used lift. It just didn't guide the lift. It used lift to improve its performance at Mars. So we're taking pieces of history, perhaps reaching all the way back down to the Wright brothers, and we're using those in a novel application for us. Yes.
Okay, let's get the mic to John Johnson right there. And please go ahead and,
Since you nerded out on that last one, do you mind nerding out on the tungsten weights to explain that a little bit better, how it guides itself that way?
Certainly. Symmetric aeroshell, symmetric body, if the center of gravity, and shaped such that it's statically stable aerodynamically. So that is to say, if the center of mass were right in the center of the body, and it was coming in like this, it would have zero angle of attack. We put 168 kilograms of tungsten in 6 slugs of 168 divided by 6, whatever that number is, about 30, here, and that moves the CG, the center of gravity, and so the vehicle tilts a bit. Its static equilibrium point, its aerodynamic equilibrium point is at an angle of attack. That angle of attack means that there's a differential pressure across the bottom. That differential pressure results in a lift. I'm feeling I'm over-nerding.
All right, we've got time for a few more questions if anybody has any here at JPL. Has everyone had a chance to ask a first question? If so, we'll go back to Irene Klotz over there.
Thanks. I was just curious if there was any thought given to, instead of using just a dead weight, to actually putting something that might be scientifically or educationally useful instead of that tungsten.
Well, I know 160 kilograms of tungsten who think that they're doing just a dandy job. Thank you very much. Certainly, we have speculated and thought of different ways of doing it. It feels, some folks think it's a tad wasteful to be hucking off this inert mass. Inert mass ends up being some of the least expensive mass to put on Mars, you know, chunks of tungsten, as opposed to kilograms of engineered or other, you know, complex pieces. We studied and traded many different methods of developing that lift, including moving mercury around inside the heat shield, having aerodynamic fixtures on the other side to develop lift. And this was the simplest, most reliable, and most cost-effective method for us to get the job done.
If you're asking the question as to whether or not you could have put something meaningful in that spot, the problem is once you eject it, you've got to land it itself land safely, and then you've got the communication issue of how does it talk back to us, and those are all very, very difficult engineering problems that really are not the main focus of the mission, and so those things tend to get avoided in that kind of a discussion.
Thanks. And Doug, could you just address the significance of this success of this mission with regards to the planning ongoing for what's going to be coming down the pike?
Sure. Well, there's an engineering impact and there's a scientific impact. The engineering impact is the ability to get a metric ton to the surface. The studies we've done over the years and that the current planning team is doing, really we haven't come up with missions in the robotic science community that really need more than this kind of a mass delivery to the surface. So I think what we have is a workhorse for the future. And that's been developed from starting with Pathfinder, working through the MER missions, and that includes software advancements that we've made for navigation, auto navigation, things like that. So that's one important feature of this. The ability to rove longer distances, longer lifetimes on the surface, more advanced instrumentation, et cetera, all play into that. Scientifically, the Mars Science Laboratory and the Curiosity rover itself specifically, it's a transition mission from follow the water of the last decade to seeking the signs of life and heading towards sample return, which is what the National Academies of Sciences Decadal Survey recommended as the next major step in the exploration of Mars and the exploration of the solar system. This mission, including, so scientifically, it bridges that gap with habitability analyses. Back to the engineering, it also helps us bridge that gap as well. With a 1-ton capability to the surface, we can actually implement those types of missions as we move forward. So all of these things really feed the advanced planning team that's working now to come up with options and approaches for the next decade. So all of these things will get factored in.
Okay, we have a question over here, fourth row back in the orange or coral sweater.
Hi, I'm Elizabeth Landau with CNN. I was just wondering, this is also for Doug, if there have been specific engineering improvements so that this rover won't get stuck the way that Spirit did?
That's really better for Pete to answer. Okay. Sorry, Pete, but...
That's okay. Well, trafficability, what we call trafficability, which is this problem, is a subject of a lot of work and studies on our standpoint. So we actually have a Scarecrow, what we call a Scarecrow Rover, which is a test rover on the Earth, which has been offloaded, off-weighted, so that it operates with a Mars level of gravity and force. And we've taken to a bunch of places out in the deserts and the dunes and things like that to be able to characterize its performance in difficult terrain. So I think we have a pretty good, and we have a Mars yard up here that you may be able to see during your stay here that basically has rocks and hills and sand and things to basically handle that. The most difficult problem, of course, is recognizing that you've got a problem before you get into the problem. And we have studied the Spirit situation, not only the last incident, but also the incident at Purgatory that occurred a few years ago. The Spirit incident and then the Opportunity had the Purgatory incident, to understand exactly how we might find such occurrences ahead of time, how we might avoid them, those kinds of things. And I think we have a pretty good handle on those kinds of things. We also have a pretty hair trigger with respect to our fault protection. I mean, the first sign you're in trouble is when your wheels are moving, but you're not moving, and you get high slippage events and those kinds of things. And we have developed algorithms to basically sense that and to stop. And so I think we're in pretty decent shape with respect to trafficability issues. At least we certainly have tried.
Yes, so let me add a little to that. I mean, this is why we do a program where you think about the missions you're going to fly and what they're going to do, and you grow technologically in this case, but scientifically also. the things that these guys have learned in Spirit and Opportunity have been applied, including the software I mentioned a bit ago. But I mean, we certainly wouldn't want to run into these types of issues with a rover of this magnitude the first time. So we learn so much each time we do this, and every time we do it, we learn more and we apply it to the next one. So that's the value of a continuing program where you can go every opportunity or every couple of opportunities and build on those experience bases. And that goes for the team as well. So there's a lot of heritage in the folks that are actually on the team, and they understand how to deal with these situations. Many of them have seen them before from Spirit and Opportunity. And so you build a knowledge base, a core competency, if you will, that becomes irreplaceable. And we've got it. We're the leaders in this capability in the world, and we want to maintain that. And it's crucial to continue doing these types of missions to be able to maintain those capabilities. It's not like riding a bike. You do lose it if you don't use it.
Do we have any more questions here at JPL? Yeah, let's get the mic over to right there. You got her.
Alicia Chang from AP. Question for Doug. With regard to the Mars exploration planning, how soon do you expect to release this new roadmap? And, you know, what are the chances of another landed mission this decade? And, you know, how will the success of, or lack of, from this current mission, Curiosity mission, affect the planning?
The team will be done with their report in August, and at the end of August they are planned to brief us at NASA on what their findings are and provide us those findings. We are putting a schedule together for when we go public with that report. It will be a public report. That report will probably be in a view graph form. The fancy color glossy version of that everybody likes to put on the shelf will be a couple months later. But we will go through and brief, obviously, the Executive Office of the President, we'll brief Congress, we'll brief the communities, we'll brief the media once we have that report in our hands at the end of August. Next opportunity for a landed mission. The budget in 18 is thin. Per the President's 13 budget. It probably can't support a rover or a lander. However, a rover is the next logical step after MSL. We have the orbiter in 13, which is Maven, and nothing in 16. However, that's balanced not just with budget, but balanced with infrastructure. All the information that you're hearing about us getting back from MSL, whether it's during EDL or on the surface, virtually all of it comes back through the orbiters. So we have learned, we have created a monster. We have developed a network of communication capabilities that give us insight, both engineering insight and scientific insight, like we've never had before at another planet. Big pipes of data. We would not really want to go to the surface with a surface mission and use the soda straw that is direct to Earth. So that has to be factored into what that first mission is as well. So once we get all the pieces of the puzzle and we work it out, then NASA will be the one that makes the decision of what that roadmap actually is that we'll go forward with. When we are public with that will depend on how long it takes us to come up with that, as well as the discussions internally within the agency and within the Executive Office of the President, since it will all fit into the 2014 budget process.
Okay, and we do have time for another quick question. Let's get the mic in the second row here. And can you please state your name and affiliation?
Steve Gorman with Reuters. So once the lander, the rover's on the ground and it's checked, goes through all its checkouts, which I understand will take a number of weeks. How long do you estimate, roughly, would it be before Curiosity is sort of ready to begin its scientific experiments in earnest? I realize that every time you move something, you're collecting some data, but in terms of the thrust of its scientific mission, how long do you think it'd be before the rover's ready to start that in earnest?
Well, we will be doing science right away. I mean, we have medley science coming in, and we are doing descent imagery coming in, and we'll be beginning to play those pictures back after a few days. In terms of the remote science, we'll be doing some of that, except for the ChemCam right away. The contact science will occur somewhere between 2 weeks and 3-4 weeks later, depending upon how the checkouts go. The sampling science, the actual taking of a sample and ingesting it into the Chemin or the SAM, probably between a month and 2 months after we land. Those are all very rough. This is a very complicated beast. It is much, much more complicated than Spirit or Opportunity in terms of the interactions amongst the various pieces and the things you have to keep track of in order to operate it successfully. We have a tremendous reliance on the orbiters. I mean, and as Doug mentioned, for data communication with us, and the orbiters don't arrive over our station at the same time every day. So things keep moving around in a very dynamic way. So it's going to be when we land, I think that we're going to go through a novel educational experience about, oh, that's what we did. Okay, did we really build it that way? Boy, that wasn't the right thing to do. Anyway, and we'll go through that. And so I think it's going to be a very slow process in kind of getting us ready to do nominal science. We've worked very heavily with the science people on what to do. We put an intermission in place to provide some opportunistic science about 10 days out. So we've tried very much to fill these blacks in, but I think we all need to exercise caution. The speech I make to the team is to recognize that on Sunday night at 10:32, okay, we will have a priceless asset that we have placed on the surface of another planet that could last a long time if we operate it correctly. And so we will be cautious as hell about what we do with it.
Okay, on that important note, we're going to wrap up the Q&A and the news conference, and we will be replaying the visuals from this news conference immediately afterwards. And just a reminder that there is a lot of useful information online at www.nasa.gov/Mars, and that includes a schedule of events coming up in the next couple of days and updates. So also the press kit, a lot of stuff there. And I want to thank our panelists, and thanks everybody for joining us today.